It's impossible to overstress the importance of monitoring your batch jobs. By monitoring, I mean checking whether the job is running, if it completed successfully, when and why it terminated, and whether the job is using resources appropriately. All too often, we see users who are perhaps new to Biowulf or new to clusters who get on the system and submit a large number of jobs without having tested sufficiently and without having considered the resources required by these jobs. They end up overloading or underloading the allocated resources. Or maybe the jobs exited immediately because there was a typo in the batch script. Or maybe the jobs ran for 2 days, but then terminated unexpectedly because they ran out of wall time or disk space. Beyond these scenarios, unmonitored jobs can cause issues for the system as a whole. So in this video, I'm going to give you an idea of what to watch out for in terms of monitoring your jobs and show you some tools for job monitoring. So first of all, what exactly does one need to monitor? Before the jobs run, you want to make sure that you have enough disk space for the temporary and output files for the job. During and after the runs, you need to check the CPU utilization, the memory, and the wall time. If you submitted the same kind of job several times over and it's run successfully and you refine the CPU, the memory, and the wall time that you request, then it's probably safe to monitor it a little less closely. But probably every time you submit a large number of jobs, you want to check the disk space situation. It's the user's responsibility to monitor his or her own jobs. The system staff may contact users if their jobs are causing issues for the system as a whole, but problems with the jobs themselves are for the users to determine and fix. So first, let's talk about CPU utilization. The first thing you need to know is whether the programs within your batch script are single-threaded, meaning there's only a single process running a single thread, multi-threaded, that is, a single process with multiple threads running on a single node, or a parallel program that's capable of running on multiple nodes. If these terms are confusing, you might want to go back and rewatch the first video in the Slurm batch system section. So how do you determine whether your programs are single-threaded, multi-threaded, or parallel if you don't already know? The Biowulf web pages for most applications will mention the type of application. And for other applications that you install yourself in your own space on Biowulf, you might need to check the documentation for that program. A single-threaded program can only use one CPU on one core. Therefore, there's no point in allocating more than one core. The default allocation is one core, that's 2 CPUs. So if you run a single-threaded program on the default allocation, you'll probably find that one CPU is sitting idle for the duration of your job. And that's okay. If you have a large swarm of jobs, you might want to improve the utilization by using the -P2 flag that was described in the swarm section so that you utilize both CPUs on your allocated cores. For a multi-threaded program, we recommend starting with 4 or 8 CPUs. And ideally, you'd run some tests to determine the most appropriate number of CPUs. If the program runs 5% faster on 16 CPUs than on 8 CPUs, meaning you've doubled the CPU allocation but not doubled the performance, then you should submit to the 8 CPUs rather than 16. For a parallel program, benchmarking your own script is highly recommended, and this is described further in the video on parallel multi-node jobs. So that's CPUs. What about memory or wall time? A common question is how to determine these in advance before submitting the jobs. For many bioinformatics or genomics programs in particular, you might have no idea how much memory the job needs or how long it will run for, especially if this is the first time you're submitting a job of that particular type. So the general procedure is to submit a single job with a generous memory and wall time request. Once the job finishes successfully, check the CPUs, memory, and wall time used by the job, and use those values to determine the resources to request for future such jobs. There are quite a few tools which you can use to get data about your jobs. There's check quota, which you've already heard about, which will give you info about your disk usage. If a job fails, the first thing to check is the .o and the .e, the standard error and standard output files from that job. Then there's sjobs and sq, which show the status of jobs, whether they are running, pending, or have exited. Jobload is a command line tool to show the instantaneous memory and CPU usage while the job is running. JobHist is another command line tool to report the memory and wall time utilization after the job ends. And finally, the user dashboard will provide details about the CPU, memory, and wall time usage both during the job as well as after the job completes. In the following slides, we'll discuss and demonstrate these tools. SQ. SQ is the built-in Slurm command to view the status of jobs. What's shown here is the default output. It shows the job ID, the partition a job is running on, the name of the job, the name of the user who's running the jobs, and the state of the job. These are all PD, meaning they're in pending state before they've started running. The time, of course, these are pending jobs, and so the time is 0. The nodes requested by this job, and the reason. Sometimes SQ might show a reason that the job is still in pending state. And these are pending because of a dependency. They're dependent on some other job completing. SQ by default will show you all the jobs on the system, which is probably not what you want. So you probably want SQ-U and your username. sjobs is a Biowulf utility that provides more information than the default SQ output, but it's slower. So in addition to the SQ output, sjobs shows you the runtime, the nodes, the memory request, that is the amount of memory requested by the job. It shows you any dependencies and features requested by the job, as well as the nodes on which the job is running. Beyond the two shown here, SQ has lots of options. You can set up your own alias for SQ to show the fields that you're most interested in. If you check the Slurm documentation for SQ, you'll see the format to request a particular set of fields in your output. So SQ and sjobs show the status of your jobs at any time. The jobload command reports the CPU, memory, and wall time usage of running jobs. Before a job starts or after it terminates, jobload will not report that job at all. The command jobload-u and a username will report all jobs owned by that user. And here's an example. In this case, it shows that the user has 2 jobs. Each of them is a multi-node job with 1 line for each node on which the job is running. It reports the time, the elapsed time, and the wall time requested by this job, the nodes on which the job is running, and then it reports the allocated CPUs and the number of threads running on those CPUs. The number of threads divided by the allocated CPUs produces the load, which in this case is 50%. And that means it's likely to be a molecular dynamics job because it's running on multiple nodes, and it's for MD jobs running only 1 process per core is quite okay. So in terms of CPU, this is a very well-behaved job. It's running steadily at a load of 50%, and that's just right for an MD job. Jobload also reports the memory used and allocated by the job. In this case, the allocation is 56 gigabytes per node, and the job is using between 8 and 9 gigabytes per node. So you might instinctively think that this job has over-allocated memory. But in fact, we know that these nodes have 56 CPUs. So the job is using all the CPUs on the node, and therefore it might as well allocate all the memory on the node as well, because that memory would anyway not be available to other users. You can also type jobload -j and a job ID to get the jobload output for one particular job. Some users who run parallel MPI jobs that SSH from one node to another to set up processes may notice that their jobs show 0% load. This is an undesirable feature of job load, and we're hoping to fix it in the future. If you have questions about whether this is meaningful and whether your jobs really are running at 0% load, please let us know and we'll look into your jobs for you. Once your jobs have completed, you might want to know how much memory they actually used, so that you can determine how much memory to request in future when submitting similar jobs. And for that, you can use the jobhist command. The command is jobhist and a job ID, and this is what the output looks like. It'll report some information about the job. It'll tell you the command that you used to submit the job, which will give you also the job script that was used for this job. It'll tell you when the job was submitted, started, and ended. And the most important part is that it tells you the memory requested by the job and the amount of memory used by the job. So in this case, the job requested 8 CPUs and 2 gigabytes per CPU, so a total of 16 gigabytes of memory, and it used 0.7 gigabytes. So the next time you submit a job like this, you might choose to request only 4 gigabytes total rather than 16. You can also monitor the CPU and memory utilization of your jobs, both while they're running and after they complete, using the NIH HPC dashboard. That's at hpc.nih.gov/dashboard. Let me show you what the dashboard looks like. You get to it by going to hpc.nih.gov or any of the pages on the HPC website and then clicking on User Dashboard. Once you log in, you'll get to the dashboard page, which has 3 tabs: Accounts, Disk Usage, and Job Info. Accounts will give you some information about your accounts and the groups that you're part of. Disk usage will show you the disk usage of the areas that you have access to. And Job Info is the one we're looking at now, which shows you your previously completed and current jobs. The dashboard saves data for at least 10 days after jobs complete. Jobs that are running show up in green with a green tab, and jobs that have completed successfully show up as black. Jobs that terminated unsuccessfully show up as red. So let's look at one of the completed jobs. In this case, it's running Bowtie, which is a genomics application. It's multi-threaded, and it looks like it allocated 5 gigabytes of memory and 16 CPUs. So you can see that the memory usage increased at first and then stayed steady during the course of the job. And it used about 3.5 gigs of memory out of the 5. So that's a very good allocation. There's a little buffer in case a particular Bowtie job uses a little more memory, but it's not over allocating or under allocating memory. And likewise, the CPUs look pretty good. It allocated 16 CPUs and it ran 16 threads. And you can see that briefly it ran one thread more than the allocated CPUs, but that shouldn't be a problem. It was probably doing I/O at that point. And down below, it gives you some information about the job, when it was submitted, when it completed, where the output files are, and the batch script that was used to submit the job. Job hist on the command line gives you the same information. Here we're looking at the same job. I typed job hist and the job ID, and it tells you when it was started, submitted, and ended, the submission path where you submitted the job from, and the script that was used, and the command line that was used to submit the job. And here again you can see the job requested 5 gigs and used about 3.5 gigs for that job. Let's look at another running job. It's marked in green, and this is a molecular dynamics job. And you see it used very little memory. It used 50% of the CPUs. It's running 4 tasks on 8 allocated CPUs. And that's normal for a molecular dynamics job. Jobs that timed out, that is, the job ran out of allocated wall time, show up in yellow. And if you click on one of those, what it'll show is the job exceeded the requested wall time limit. And for jobs which show up in red, which means the job failed, then looking at the memory and CPU allocation may give you a clue as to why the job failed. In this case, you can see the problem very clearly. The memory usage keeps increasing until it hits the memory allocation, and the dashboard reports that the memory use likely exceeded memory allocation. So the next time you submitted this job, you would request more memory. Instead of 16 gigabytes, you might go to 32. Let's work our way through a few more examples from the dashboard. I should point out that all the examples shown here are actual Biowulf user jobs. So here's a job where the memory allocation was 8 gigs and it used about 3 gigs, which is fine. But look at the CPUs. The allocation was 32 CPUs, but the job used about 4 CPUs. So in this case, we would strongly recommend that the next time this job was submitted, the CPU allocation should be reduced to 4. Here's another job. The memory allocation was 256 gigs, and the job used about 50 gigs. So it would be a really good idea to reduce the memory allocation for future runs. But the real problem here is the CPUs. The allocation was 2 CPUs, but for most of the duration of the job, it ran 64 threads on those 2 CPUs. So this is a heavily overloaded job. And it would be really important for the performance of this job to increase the CPU allocation the next time. This job is a little more unusual. For some period of the time during the job, it ran about 64 threads on the allocated 8 CPUs. Now, if this was only a small part of the job, if the job was now going to be using 2 CPUs for another 24 hours, you would probably leave the CPU allocation as it was. But if this was the entire job that you're seeing here, it looks like it was overloaded for a fairly significant portion of its run, and so you'd probably want to increase the CPU allocation to 56. Here's an example of spiky CPU usage. Periodically, the number of threads goes up to 40 on the allocated 2 CPUs. So overall, looking at this job, it looks like for a fairly significant proportion of its time, it was running 40 threads on 2 CPUs. So you probably should increase the CPU allocation to 40. And here's my last example. This job used the default allocation of 4 gigs of memory and 2 CPUs. That's 1 physical core. The memory usage was very low. The CPU usage was 1 throughout the run of the job, which means it was probably a single-threaded application. So if this was a solo job, a one-off, it would be perfectly okay as is. But if this job was part of a swarm, then for each of the swarm subjobs, you would have one idle CPU out of the 2 allocated CPUs for that subjob. If you have 1,000 subjobs in the swarm, that's a significant number of CPUs sitting idle. So you could double your throughput by trying the -p2 flag. And what that would do is pack 2 processes, that is 2 lines in your swarm command file, onto the 2 CPUs of the 1 physical core that's allocated to each subjob. So you'd have twice as many processes running at a time and twice the throughput. Now this may not work perfectly for all applications, so you'd have to test it and see if it actually improves your overall throughput. But it's probably a good idea to try it.